Leeds International School, Form 5, Lower, Physics, First Term, Chapter 14, Energy Transfers. This covers the specification 4.1 to 4.5. While watching this video, please refer your textbook, page number 133 to 137. Learning objectives. 4.1. Use the following units: kilogram, joule, meter, meter per second squared, Newton, second, and watt. 4.2. Describe energy transfers involving energy stores. Energy stores: chemical, kinetic, gravitational, elastic, thermal, magnetic, electrostatic, and nuclear. Energy transfers: mechanically, electrically, by heating, and by radiation. 4.3. Use the principles of conservation of energy. 4.4. Know and use the relationship between efficiency, useful energy output, and total energy output. 4.5. Describe a variety of everyday and scientific devices and situations, explaining the transfer of the input energy in terms of the above relationship, including their representation by Sankey diagrams. Units. Kilogram. It is the base unit of mass in the International System of Units, the current metric system, having the unit symbol kg. Joule. Its symbol is capital J. Unit of work or energy. It is equal to the work done by a force of 1 Newton acting through 1 meter. Meter. A meter is a metric unit of length. It's equal to 100 centimeters. Meter per second. The meter per second is the unit of both speed and velocity. Meter per second squared. It is a unit of acceleration. Newton. Its symbol is capital N. A Newton is the international unit of measure for force. 1 Newton is equal to 1 kilogram meter per second squared. Seconds. The second is the base unit of time. Watt. Its symbol is capital W. Watt is the unit of power. Okay, let's remind what is energy. Yes, energy is the crown for physics. It is found in every branch of physics. Energy is the capacity of a physical system to perform work. It means the ability to do work. Energy is the capacity of something to do work. If something contains a store of energy, it is able to do work. If something does not store energy, then it will not work. For your IGCSE, you are expected to know about 8 different energy stores. Let's see what are they. Stores of energy. First one is kinetic energy. Kinetic energy of motion, observable as the movement of an object, particle, or set of particles. Any object in motion is using kinetic energy. A person walking, a thrown baseball, a crumb falling from a table, and a charged particle in an electric field are all examples of kinetic energy at work. Next one is gravitational energy. It is the energy stored in an object as a result of its vertical position or height. The energy is stored as the result of the gravitational attraction of the earth for the object. Next one is elastic energy. This is the energy stored in something that has elasticity, where the object can stretch and compress. Balloons, rubber bands, bungee and trampolines all have elastic potential energy. Next one is electrostatic energy, the energy due to the force of attraction or repulsion between charges. Magnetic energy. It is a force that exists between two magnetic poles which produces magnetization. Electrical currents produce magnetic fields just and similarly. Magnetic fields always exert forces on electrical charges in motion. Next one is chemical energy. It is energy stored in the bonds of chemical compounds like atoms and molecules. This energy is released when a chemical reaction takes place. Usually, once chemical energy has been released from a substance, that substance is transformed into a completely different new substance. Next one is nuclear energy. It is a source of power which is created from energy released by a nuclear reaction. An example of nuclear energy is the electricity generated by a nuclear reactor, which is a major power source used in Japan. The last one is thermal energy. It is the energy that is generated and measured by heat. An example of thermal energy is the kinetic energy of an atom. An example of thermal energy is the chemical energy in a molecule. Let's summarize the stores of energy. Kinetic energy, the energy of a moving object. Gravitational energy, the energy something gains when you lift it up and which it loses when it falls. Elastic energy, the energy of a stretched spring or an elastic band. Electrostatic energy, the energy due to the force of attraction or repulsion between two charges. Magnetic energy, the energy due to the force of attraction or repulsion between two magnets. Chemical energy, the energy contained in a chemical substance. Nuclear energy, the energy contained within the nucleus of an atom. Thermal energy, the energy something has due to its temperature. Let's see some examples of some pictures to understand stores of energy. Kinetic energy, gravitational energy, elastic energy, electrostatic energy, nuclear energy, magnetic energy, chemical energy and thermal energy. Let's move to the topic energy transfers. Energy is transferred by one of the following four types of energy pathway. In addition, there are four ways in which energy can be transferred between those stores. Mechanical work, a force moving an object through a distance. Electrically, charges moving due to a potential difference. And heating due to temperature difference caused electrically or by chemical reaction. Radiation, energy transferred as a wave. Example, light infrared sound. The sun emits light radiation and infrared radiation. This picture shows some examples of energy conversions in our day-to-day life. Next, we are going to move the conservation of energy. The law of conservation of energy is a law of science that states that energy cannot be created or destroyed but only changed from one form into another or transferred from one object to another. The law of conservation of energy states that energy cannot be created or destroyed. It can only be moved from one store to another. What this means is that the total amount of energy in a closed system remains constant but can change where it is stored. For example, a gas cooker heating a pan of water takes energy from the chemical store of the gas and transfers it to the thermal store of the water. Let's see some basics about energy. Whenever energy is transferred from one store to another, some of that energy is usually wasted, either ending up in a thermal energy store or being transferred away from your system as radiation. It means as light or sound. The efficiency of a system is the percentage of energy transferred from the original store that ends up in the intended store. Efficiency can be calculated using the following equation. Efficiency is equal to usual energy output divided by total energy output and multiplied by 100%. Sankey diagrams. The efficiency of a system can be represented using a Sankey diagram. This is a structure of Sankey diagram. Total energy in, useful energy output and wasted energy. The end of the arrow pointing to the right represents the energy that ends up in the desired store. It means the useful energy output. The end that points down represents the wasted energy. The width of each arrow is proportional to the amount of energy going to each source. Let's see an example. This diagram shows the energy transferred by an electric heater is in 1 second. See the diagram. Please study the diagram. When you are using an electric heater, thermal energy supplied by the electric heater is 50 joule. Thermal energy raising the temperature of the water is 38 joule. Now you want to calculate the amount of wasted energy. It's 12 joule. You can calculate it. Subtract 38 from 50 joule. You can get 12 joules as wasted energy. Let's learn some exam tips for your exams. The concept of energy stores and energy transfers is a fairly new one, and so there is a chance that you might have been taught this topic slightly differently. Don't worry if you have, but you will need to become familiar with the topic as presented here, as this is a approach that will be used in your exam. Drawing good Sankey diagrams takes practice. Start by planning your diagram. How wide are you going to make the input arrow? How wide will the useful energy out arrow need to be? How wide must the wasted arrow be? Next, start drawing the diagram one step at a time. Draw the left hand side of the arrow along with the line going across the top. Next, add the useful energy out arrow, making sure it is the correct width. Now carefully mark the start and end of the wasted arrow. Make sure your marks are the correct distance apart. Finally, join the markings together, finishing the wasted energy arrow. Thank you for watching the video.